Alright, I was off camera for most of that. Don't care. I'll try and do better this time. Angular momentum. We were talking about L equals m times v times r. Yeah, that should be good, but now I'm standing right in the way. We were talking about L equals mvr for a point object that's revolving around some central axis. For other shapes, okay, for other objects, we have the following. And actually what we're going to do is we're going to compare this to the old linear momentum formula. You guys know what that is? P equals mv. Linear momentum, symbol is P. Angular momentum, symbol is L. I'm going to skip over m for a second. Linear momentum, P equals mv. V is linear speed. The symbol for angular speed is omega. And then m, it's not really such a thing as linear and angular mass, but in linear equations, we usually use mass. We're talking about something rotating. We don't care just about the mass. The shape also matters. What we're talking about is the moment of inertia. Here is the equation for angular momentum for an object, any object that's not just simply a point object. L equals I omega. Actually, it turns out if you were to plug this in here, you can reduce down to this. I'm not going to go there right now. Okay. One of the big things that we talked about when we talked about linear momentum was that if we have an object that has no net forces on it, then that object has its momentum conserved. Okay, the momentum does not change. Kind of a similar thing, or exactly a similar thing, with angular momentum. If an object is what we call free to rotate, okay, if nothing's holding it in place, okay, it's not like, it can rotate, if the torque is put on it, it starts to rotate. Another way of saying that is if there is no net torques acting on object. If that is the case, if the net torque is 0, then L is conserved. The angular momentum cannot change unless there is a torque acting on the object. And as a matter of fact, if there is a torque, this should also look kind of familiar. If we do have a net torque acting on an object, that net torque acts for a certain amount of time, it will change the angular momentum. That should look really familiar. This is the same as F net times T equals J, or delta P, impulse or change in momentum. Now, since we're talking about something rotating, the net torque, multiplied by the time will change the angular momentum. Okay? So there's a little bit about angular momentum. Before we get into a really interesting problem, and I say interesting from the physics perspective, I think it's a great problem. You may or may not, but it more closely applies to real life than the things you've been doing, which is nice. We have one more thing to talk about, which we'll talk about more in the next set of videos, and that is rotational kinetic energy. Now, it's very important we talk about this because we've talked, think about all the other things that we've studied this year. With the exception of waves and electricity, all the motion stuff that we've studied, we've now covered in terms of both something that linear motion and angular motion. Last one we have to cover is energy. So, rotational kinetic energy. The kinetic energy you're familiar with is called translational kinetic energy. It's the energy something has from moving place to place. Well, it turns out that something that rotates also has kinetic energy. Parts of it are moving from place to place. But it is not as simple as just doing 1/2 mv squared. Okay? Rotating objects also have kinetic energy. Rotating objects have K, kinetic energy, even if they are not translating. And again, translating just means moving linearly. even if they're not moving linearly, they can still have some kinetic energy. The formula for rotational kinetic energy is as follows. K, I'm just going to put K ROT for rotational, is equal to, well, let's see, if it was 1/2 mv squared for translational kinetic energy, instead of an m, hopefully you see where this is going, we're going to write an I, and instead of a v, we're going to have an omega squared. Okay? And this doesn't replace kinetic energy entirely. Matter of fact, in our next little mini topic, you will see objects that have both translational kinetic energy and rotational kinetic energy. An example is anything, where's I don't know where that bouncy ball went, probably hanging out over there somewhere. Something that rolls. Expo juice, I guess, okay? This is translating. It's also rotating. It has both translational and rotational kinetic energy. Okay, nothing wrong with that. Objects can have translational kinetic energy, obviously, 1/2 mv squared, and rotational kinetic energy at the same time. For example, objects that roll. And I remember something in college where you're not really supposed to make a distinction, like there's only one type of kinetic energy, it's energy associated with motion. You're not really supposed to treat these as two different types of kinetic energy, but I never really understood that. I mean, an object's kinetic energy is its kinetic energy, okay? Some of that happens to make the object move, some place to place. Some of it might happen to make the object rotate. I don't really see a big, as long as you understand that kinetic energy just means, hey, something's moving. It's either moving side to side, or it's moving, or it's rotating. That's all I really want you to know. Now, here's where, so the angular motion and the rolling stuff we will get to later. But here's where all that torque and dynamics and moment of inertia stuff, here's where it all comes into play. I'm going to give you a little example. I'm going to zoom out a little bit first so I can get this set up correctly. Okay, I can zoom out a little farther. Okay, and just a little. Alright. So here's the picture I want you to draw. Here's the example we're going to look at. It's an example you should be fairly familiar with. Okay? Let's see here. I'm going to draw this. And you're going to want to write small. We have a lot to write for this one. Okay, so we have a pulley system. The string connects two blocks, one of mass 2m. It rests on a frictionless table. String passes over a pulley. It's connected to a block of mass m that is hanging some distance above the ground. Now, here's what I'm going to do. I'm going to show you the regular way we used to treat this. Okay, we're going to solve for things like the acceleration of the system and the tension in the rope. Then we're going to solve it using the principles of torque, and I'll explain why you have to use one, why you have to use the other in certain cases. The way we would start this, when we learned how to do this, was you would draw two free body diagrams. First, for mass of 2m, you have tension, you have a normal force, you have a force of gravity. I'll put Fg2 for the mass of 2m. You have a little axis, x, y, plus. And then for the hanging mass of mass m, you have tension, you have force, gravity, 1, I guess. And if the 2m mass moves to the right in the positive x direction, we should set up our axis so that the positive x direction for this would be aligned with what happens to this block if the 2m mass goes to the right. 2m mass goes to the right, this block goes down. Let's call this direction x, this direction y. There we go. Now we need net force equations. For this one, F net x equals tension equals m. I guess for right now I'll call it m2ax. and then we really know that this is 2m ax. And in the y direction, I suppose we'll write it anyways. F net y equals Fn minus Fg2 equals m2 ay. We know it's not accelerating in the y direction, so we have Fn equals m2g. Fn equals 2mg. Over here, for this object, we have F net in the, x direction is Fg1 minus tension equals m1 ay, ax. This ends up being m1g minus t equals m1 ax, or mg minus t equals m ax. Now the things that we know, the acceleration in the x direction, this has to have the same acceleration as this. We assume the rope does not stretch, okay? We assume this is a non-stretchy rope. We assume that whatever this acceleration is this way is the same as this acceleration this way. We also assume the tension is the same in both cases. So what we have right now is a situation where we have two unknowns, two equations, okay? We don't know the acceleration, we don't know the tension, but we can solve for those things. I already know that the tension is equal to 2max, and with the assumption tension is the same everywhere in this string, then I can make this substitution. I take this, I bring it in, I say mg minus 2max equals max. I add that to the other side, I'm left with mg equals 3max. Cancel my m's. If I solve for ax, I get g over 3. Then I could even go back and I could plug that in for my tension equation. Two mg over 3. I just bring the 3 to the front. I say the tension is 2/3 of mg. I am going to basically put all of this in one section over here. This is how you used to deal with this problem. And it is still okay to deal with this problem if some conditions are met. The key thing that makes the difference here is actually this pulley. Because before, we were always told with these problems that it was a light, frictionless pulley. Light meaning very low mass or no mass, and if there was no friction on the axle, the pulley was free to spin. Well, guess what? In the real world, pulleys have mass, and there's probably some friction acting on them. We're actually not even going to deal with the friction part, but we're going to assume the pulley has mass. And that is not really great, okay? Not great from the sense that it just makes things a little more complicated. We can still deal with it, but it does make things a little bit more complicated. We're going to write ourselves a little notes. If pulley has rotational inertia, what that really means is, does it have a negligible mass? Does it have some mass? Okay? The reason being, if it has mass, then if it's rotating, it definitely has a moment of inertia. Because a moment of inertia is some coefficient times m times r squared. So if it has some mass, it has rotational inertia, and unfortunately, we cannot simply just sum the forces. We can't just take the sum of all the forces. If this happens, we have to do both the sum of the forces and the sum of the torques. If the pulley has some rotational inertia, it's not just going to rotate for any old force. It might, but there are torques that make this pulley rotate. Okay, there are forces that will cause it to rotate, and the size of the force will depend, or will tell us, and where it's applied, and the angle that it's applied at, will tell us how it causes the pulley to rotate. And that's actually important. So, a pulley. I don't have one on my desk readily, but you know what a pulley looks like, or like the little spinny part of a pulley. It's a disc. And it turns out that the rotational inertia for a disk has this equation. 1/2, that's the coefficient, m r squared, where the mass of the disk is m. And I said r is some important distance. You can probably guess that r for the pulley, this little disc that's rotating, r is the radius. Radius equals r. Okay? So, if we're told that the pulley has a mass, if the spinning disc part of the pulley has a mass, our problem just got more complicated. We now have to deal with the torques that act on this. Okay? That's part one. We have to deal with some of the torques. Now, here's the interesting part. If this happens, we also can no longer assume that T is constant throughout the string, which is unfortunate. But it makes sense. The string acts on the pulley in two places. The same distance from the axis of rotation in both cases. Axis of rotation is through the middle. If you had a tension that was the same in each place, okay, here and here, same force, same distance from the axis of rotation, same angle, it's going to, I'm going to tell you right now, it's going to be sine of 90 equals 1, you would get two torques that are exactly the same trying to cause it to rotate in opposite directions. Nothing would happen. There would be no rotation. But if the pulley rotates, that means the tension on one side has to be greater than the other because one of the torques is now greater than the other. So, we no longer get to assume that the tension is the same throughout the string. The reason being, if it was, the pulley would not rotate. Okay? So we're making we got some new assumptions we got to work with. Okay? Now it's time to do a little bit of math. The nice thing is that we kind of already have the free body diagram set up. We don't have to change the free body diagram. Actually,